And let's see. Okay, so we were talking about navigating this plane last time. We said we could design our reactor systems around these kinetics. So in effect, this was what nature is doing, right? You've got, given a certain conversion that will result in a certain concentration in the reactor, and given a certain temperature, that will define the reaction rate. So with your concentration and your temperature specified, right? If you pick a point here that specifies a conversion and that specifies a certain temperature. So C, A, and T are defined when we pick a point. If so, the reaction rate is also defined. And we find that at different points, we have different rates of reaction. We were doing all this in the context of a reversible reaction. So that's why we found at a certain stage, we had equilibrium, right? That as we moved around on this plane, there came a point where we were at equilibrium. We said also that we might specify an inlet temperature. So for instance, if 300 is an inlet temperature, and if we were to draw an adiabat, that we would progress up and we would reach some point depending on the volume of the reactor. So for a CSTR, as we increase the volume, we would be achieving higher conversions. But there is a limit to how high the conversion can be, and that limit is dependent on the inlet temperature. So we can see here that for an inlet temperature of 300, we are limited to a maximum conversion of something like 0.48. And then we can choose a different inlet temperature. And if we choose one, say here, we can see we've got access to a higher conversion and so on. And we also said we could control what line we were operating with by changing the inlet temperature. And we can do a simple practical thing towards that. We can simply change the inlet temperature there. I'd like to take a second and just ask you to think, what could we do to change the gradient of this line as well? Any takers there? How can you, we've talked about, in effect, moving the intercept of the straight line. And maybe we should talk about what that means. Let's see where are. So I think we have this, yeah. So remember, this is of the adiabat. We have available to us the adiabatic line. Okay, let's just write it. So we have available an adiabat. So we can say the conversion equals, and we had minus, and it was the sum I C P CPI, and that was times the inlet molar flow ratio. So theta sub I, and then all this divided by the heat of reaction. We use sub most of the time. Okay. And this was times T minus T in. So our energy balance gave us this equation when we didn't have heat added to the process, right? So that is how our conversion would change with temperature according to the energy balance. Just checking in the chat. So Jaden, changed the inlet temperature. So that's one thing. If you change the inlet temperature, then that's going to shift this line left and right. But I'm saying it's a straight line. We can say there are two variables. Number one, the intercept. So yes, definitely changing the inlet temperature will move that intercept. But what about the gradient, right? That's the other parameter of our straight line. And we can see here, we do have a straight line, right? This is conversion directly proportional to temperature. We know that heat of reaction is actually a temperature function. But if we make the approximation that it's about constant, then this whole thing is a constant times T equals X. So this is a straight line of X in T. So it's a straight line, it has an intercept, and as you say, Jaden, as we change that T in, it's going to move that intercept. But what about this gradient? Any ideas for changing the gradient here? Right, just looking at this equation, any way we can change the gradient? So I'm a fan of long unequal. Yes, please go ahead.
So I just wanted to ask, what is on the y-axis? What variable is on the y-axis of the?
So we can see here conversion. So that's
conversion.
On the y-axis, and temperature here.
So my understanding is obviously the formula for gradient is y2 minus y1 over x2 minus x1. So if we change like the temperature used to create the line or the conversions and the corresponding conversion, would that not change the gradient?
Well, the temperatures here, you see, as you change this temperature, then X will change automatically. It's not the case that you can change the gradient just by changing T, because when you change T, X is also going to change, and it's going to change according to this equation. So the best way to look for a gradient is, strictly speaking, the gradient is nothing but, 1 second. Yeah. My equation to come up. So strictly speaking, the gradient is dx dt, right? Dx dt. So looking at this equation, what is dx dt? So keep going there, Akim. If you look at this equation, at this straight line equation, what's the gradient here?
Would it not be the gradient in this equation? Would it not be the sum of I theta I CPI over delta HR?
Yep. So that's our gradient. Okay. So now we are asking, can we change this gradient? So looking at this gradient now, what do we have control over in this?
Do we have control over the heat of reaction?
No, that's given to us by nature. So for a given reaction equation, we are stuck to a certain heat of reaction.
Oh, yes. And I believe that's the same with CPI. So could we change theta I?
Yes, because theta I is our inlet molar flow ratio. And so if we change the inlet flow ratio, then definitely we can change the gradient. But the way we pose the problem is that it's pure A coming in. So can we change theta I if it's pure A? So the answer to that is no. You can't. If it's just pure A being fed to the reactor, then we can't change the gradient at all. But you see, this is where our creativity as design engineers comes in. We are not forced to stay with pure A. Why stay with pure A? Why only feed pure A? What about if we want a steeper gradient? We are free to pick any inert. So, I mean, we could even put a product in if we wanted. But let's say we don't want to upset the reaction rate. We want to do this independently of changing the reaction rate. Then theta I is stuck to 1 for pure A. But then instead of just pure A, let's just add another component in our feed. So we can say we're going to add a component, So then we're going to have, we are still feeding CP. So we are still feeding component A. So that CPA is going to be what it is. But now we're going to add an inert as well. So here we will need to retain the theta. And here let's call I the inert, and then C sub P comma I. So we are adding an inert here, and then we also have the denominator. So if we add an inert, there's an extra term here. And if this inert, of course, we have to pick the inert carefully. So if we want a sharper gradient, right, and we can see it would only make sense to look for a sharper gradient because then we'd need fewer reactors to step up. So we would want to choose a high capacity inert, a high heat capacity inert. And we can easily do that. We can say, okay, what's the heat capacity of A? Then using that as a benchmark, look for things that won't react and say, okay, which component will have a high heat capacity or higher heat capacity than A? And then we can choose some ratio of that compared with A. So we are not only free to add an inert, we can also change how, so we can tailor make this gradient. We are not stuck to one gradient. So only looking at pure A, you are stuck to one gradient. But adding an inert gives us the free play to tailor make our gradient here. So just depending on the inlet flow ratio of the inert, we can totally change that gradient. And that's going to, you can see already that that's going to give us fewer stages in stepping up. Okay, any questions or comments there? So that's the first possibility. And now let's go back to thinking about how we use this information. So first off, we had said that we can identify a maximum rate path line. So if we have pure A, then it looks like that. If we have an inert and the gradient looks like this, then we can see that's going to change where our maximum rate path line is going to sit. So I'm just going to sketch out a rate path line. And let's just do it for some intermediate. Oops. Yeah, I'm so looking forward to going back to in-person. We'll be able to, I don't have to dig around on these editors anymore. Ugh. So let's just put a certain curve in for our maximum rate line. So let's say this was the maximum rate line. Okay, so that's one. And we had talked about the other criterion, namely that if you have your operating line, if you've chosen your inlet conditions, then that fixes the gradient of the operating line. And then you are limited to a certain conversion. So for a given temperature here, you are limited to a certain equilibrium conversion. And what we can do is move this line around, right? We can imagine the case where we are using a different inlet condition, then that's going to define for us a different equilibrium temperature. So let's just make this, let's extend it. So we can mark off different points along this plane, and that tells us the equilibrium points that we have. But what we actually want is 10 degrees short of equilibrium. So for a given temperature, we look up what's the equilibrium value and then take 10 degrees short of that. And then that would specify for us another point. So let's sketch a point here. So that's the equilibrium that applies there. Now let's keep moving. Let's do another one. So let's say that was our inlet. Then we can see there's another equilibrium point here. Then that's a different point. So let's draw that one. So 10 degrees short of equilibrium is somewhere here. So that's another point. So we can keep doing that. And I'm just going to sketch a line here. So let's give it that. And so we'll get a different line for equilibrium, 10 degrees to equilibrium. And then looking at these two lines, they have different meanings in terms of our design. So this so-called maximum rate path line, this is where we get the maximum rate, right? So moving anywhere beyond this line gives us a lower rate. And in fact, let's just see that. So we did say this yesterday, but let's just see that. And I actually want to move this line a little bit so that it's more correct. This was just a sketch, right? It's going to shift this a bit more. Right, so we can see here, remember, as we look along our operating line for a CSTR, we are in effect looking at different volumes of the reactor, right? If we take a very small CSTR, then there's not much time for reaction. The space-time will be very low, and so we won't get much conversion. But as we take greater volumes, there's more time for reaction and we get a higher conversion. So as we look along this line, we are effectively looking at greater volumes of our CSTR. And we can see here, there is a point where we are tangent to this line. So the reaction rate is equal to the value for this point. So this is 0.001. And then if we use a bigger volume than that, then we are actually moving closer to this red line. And the red line is 0.0001. So this is a much lower reaction rate. So it's not the case that by just increasing the volume of the CSTR that we are going to get a better reaction rate. We are going to get a higher conversion, and that is a good thing. But the efficiency of the reactor starts to go down. So you can say this is the point where we are maximizing the efficiency of that reactor. If we take any points below this, this is really a bad operating region. Any points below this, and we are moving closer to the red line, which has a lower reaction rate. So any points to the left here, it's a lower reaction rate and a lower conversion. So there's really no point to looking down here. Beyond this point, you can say that, well, here I'm sacrificing my reactor productivity for a higher conversion. So at least I'm getting a higher conversion up here. That means my separation costs later will likely be lower. So that's the kind of logic we have to think about there. But yeah, this would be the optimal point. Okay. Any questions or comments there so far? Okay. So we said if we wanted to optimize for the reactor productivity, then that is where we would stop. And then we could apply an interstage cooling. So we would cool back down here, right? And we could ask, well, why not cool back down all the way here, right? Why not cool down to 200 or even 100? And then we could one-shot this, right? We could go from this very low temperature to this nice high conversion. So the reason we don't really do that is it's extremely expensive to apply cooling on a plant, right? The moment you go even 10 degrees lower than 300 Kelvin, you have to think about a refrigeration plant. So there's a lot more work. You have to then, it's a whole other plant you have to build. You have to, as I say, a refrigeration plant where probably you are compressing and decompressing nitrogen or some other heat, some kind of fluid like that. And people do it in polymerization. I have done research with a company that was that had a refrigeration plant. So there, it was worth so it comes down to the economics. What's the cost of building a refrigeration plant versus the cost of separations that you have to do. So you typically don't want to cool to below 300 Kelvin, right? So quite often you'll see in the designs we do something like this. So we might take a point here. So we might go up to this point and then we'll cool it, but only to 300 Kelvin. And then from there, we can step up. And so we can, the gradient of the line will be the same. And so we can step up. And you can see here now, well, we only have this much to go on. If we wanted to stick to high efficiency, then your maximum rate path line tells us this is where we have to stop. So you could say, well, it's really not worth building a reactor that only does this much work, right? That only gives me less than 10% more conversion. So in this case, I'm going to sacrifice my productivity and go up to this point. Okay, so that's a design decision. So navigating this plane, it's our creativity as design engineers, but we are also watching out for constraints. We know the moment we go below 300 Kelvin in terms of where we position our lines, then that's adding significantly to the costs. Excuse me. Okay, so those are the things we can think about in the context of a CSTR. Any questions or comments there? Okay, now let's start thinking about a PFR as well. In the case of a PFR, where would you stop, right? We know a CSTR, we need to stop here because the whole reactor is operating on this point. So take a minute and just sketch out, think about different points along this line. Where should that PFR end, right? We are choosing a volume in the CSTR here. But is that also true of a PFR? Think about different points along this line. Right, so I'll give you a minute to think about that and sketch out some ideas there. Okay, would anyone like to describe their approach there? Any ideas about whether we should just stop at the same point for a PFR or a different point? So let's think about the fact that for a CSTR, the whole reactor is operating on that point, right? So we can't find other points along this line in the CSTR. So in other words, we enter at 300 Kelvin, and then the whole reactor is positioned on this point, right? 0.3, let's call it. Let's say that's 0.3 conversion. You can't find 0.2 in that reactor because it's perfectly mixed all the time. It's not as if you can find a point where the concentration is such that you could say the conversion is 0.2, right? That was the whole feature of CSTR. It's perfectly mixed all the time. So that's the CSTR. The entire reactor is sitting on this point. That's not the case for a PFR. In the PFR, we've got, we enter and we've got a certain conversion that we can identify at the point of entry. So we enter and we would say, well, here, my conversion is 0. And then if I look a little distance further along, then I've got a higher conversion here and a higher conversion. And maybe it's saturating, maybe it's not increasing as much every time. But these are different conversions that this reactor is going through. In other words, if we were to plot this, let's see if I can draw this. Yeah. So we've got a whole profile of conversions in this reactor. And by the same token, yeah, it's hard. By the same token, we also have a whole profile for temperature. So, but just talking about conversion for now, right? In the PFR, we have all these other points. So, and in fact, I should have drawn this the other way around, right? So the conversion in the PFR is going up like this. So it's much more like this. And then it's saturating at some point. So your PFR conversion is doing this. So we can see then that all these points can be found. So if this was the line that applied to the PFR, we can find a real point in that reactor where each point along this line is identified. So that's our PFR. If that's the case, does it make sense to stop here, right? This is your maximum rate point. Would you want to stop at this point then? Anyone want to say whether, okay, thumbs up if you would want to stop, if you want your exit point to be on this point here in your PFR. Or thumbs down if you don't want to. Okay, no one wants to commit. Okay. Well, you see, it wouldn't make sense to stop on this point, right? If you look in your PFR, you have managed to reach the maximum reaction rate. Now, why would you stop just when things are getting good, right? You've gotten now to your highest possible reaction rate. Why stop there? Why not keep going and let the maximum rate be the average reaction rate in your PFR? So you would rather that this point be sitting somewhere in the middle of your PFR. So for the PFR, you want to keep going, right? You want the maximum reaction rate to be the average reaction rate across your PFR. So what's optimal for the CSTR is not what's optimal for the PFR. And you could say, well, we can use the criterion that the maximum rate should be the average rate across the whole PFR. We could also say we could just go all the way to 10K to equilibrium, right? So you could just stop the PFR there. So that's typically what we do for a PFR. We go to 10K to equilibrium. For the CSTR, we could, if we really want to optimize each one, then we would stop here instead. Okay, any questions or comments there? So that's the PFR. Now, what about the batch reactor? Remember, on the batch reactor, we can exert some fine control, right? Because it's a space that you can control what happens in time. Let's say we have an inlet temperature of 300 or an initial temperature of 300, right? In the language of a batch reactor, there's no inlet, so we talk about initials there. So the initial temperature in the batch reactor is 300. Clearly, that's not optimal. How would you get to an optimal state in the batch reactor, and how would you stay there? So take a minute and sketch out some ideas towards that. So any takers there? Any ideas in the batch reactor? What could we start doing to operate optimally there? So let's think about this batch reactor, and we are starting with this initial temperature. So we are here to begin with. Now, this reaction rate, right, in the batch reactor, we are going to assume that we are applying heating and cooling here. So this batch reactor, if we do just let it react adiabatically, it will just go to this point. And then we can't really do anything unless we add heat. So in the batch reactor, remember the variable is time. So we would simply observe this batch reactor as its conversion changes. In the batch reactor, we can find all these points as well. It's just that we have to wait long enough for it. So in the batch reactor, if we are sitting at this reaction rate, then the conversion is going to rise. And at some instant in time, we'll reach a point here and we'll reach a point here. So we can see the reaction rate is going up. It reaches the maximum here. And as it keeps reacting, it goes past that point and we get to lower rate regions. So you could say, I could just operate my batch reactor in the similar way as the PFR, and I'll get to a point here. And then we could apply cooling at this point. So like with we didn't say it, but with the PFR, you can also do interstage cooling here. So if you add cooling, then you would step back here. And then you would, if you cool to 300 Kelvin, and then you're free to react further along there. So you could do that in the case of the batch reactor as well. You can let it react. And the way you would do that in one reactor is by installing a cooling unit. So let's say this was a cooling coil. So the temperature would go up. I actually use where you put this to, so this would be a cooling coil. So you perhaps wouldn't have any fluid in the cooling coil. You'll just let the temperature be rising in that batch reactor and it reaches a point there. Then when it does that, you would switch on cooling and you would look for the batch reactor temperature to go down like this. Of course, in the batch reactor, while we're waiting for the temperature to go down, we can't prevent the reaction happening. So it would be more something like this. So the reaction keeps happening and we might end up on a point like this. Or we could say, well, we are free to simulate the case. We could start cooling earlier. So we stay closer to this line like that. And then we switch off cooling and we just let the reaction proceed, and it could do that. So that's what we could do, right? With the fine control we can exert in a batch reactor, we can change the flow rate in this cooling coil to the extent that we quickly get it back here. Once it's here, then switch off the cooling coil and just let it react up there. So that's what we can do over time. Now, you could say, well, if you are able to do all that, then why do we have to wait here? Why not apply heating and cooling to get better reaction rates? Because we can see really nice reaction rates here, right? Here we've got like 100 times the reaction rate, 0.01. So why can't we, in the batch case at least, get ourselves there quickly? So if we're starting at 300, how do we get quickly into this nice high rate region? Right? And it's a single word answer. At least give me that much today, right? Anyone? what's the quickest way to get into a high rate region? Right, you can add heating. You just add heating to the system. So we've got a cooling coil, but there's nothing to stop you also putting in a heating coil. So if we do that, we've got a heating coil. Maybe we draw a heating coil like this. And we just switch on either one as we need. So we can say initially we are at 300, but it's in a lousy reaction rate region. It's between the teal and the red line. So that's quite a low rate, whereas we've got this very high rate region. So why not blast this with a short shot that's going to get us into the high rate region? So if we apply a lot of heating for a short time, then it's going to push us up here. It's going to push us into the high rate region. So we would go heating will push us in here. And of course, it's reacting as it goes. So it's not going to be a perfect flat line against the edge there. It's the conversion will be rising as we are heating, but we'll get in this range. And then the tendency of the system is always to move towards equilibrium. So the system is always trying to push us this way, which is not what we want. We want to stay on the maximum rate line. So what we should do is get ourselves to this point. And now we know going any further is going to drop our reaction rate. So we would like to stay on this maximum rate line. And so what would we do from this point on? Once we've reached the maximum rate point, knowing that our process is, our nature is trying to push us towards equilibrium, right? Nature is running down towards equilibrium. So nature's tendency is to cause the temperature to rise here. So what could we do to stay on the maximum rate path? So clearly, we can just do cooling. So we apply cooling now. And so we know in the next second, nature will try and go there. We want to go here. So we can do a small energy balance and work out what we must add, how much cooling we must apply to get onto this point. And so we would switch off heating. We don't want heating. We don't want to go past this point now. We want cooling. So we switch off the heater and we switch off heating and switch on cooling. We start passing in cold water through this cooling coil. And we do it in such a way that we stay on this line. We track this line as closely as possible, right? And so in the batch reactor, because of the fine control, we can implement a control scheme here that will get us into the high rate region quickly and then keep us at the maximum possible reaction rate. So that's how we can design the batch reactor. Any questions or comments there? And I don't know if you feel this is kind of far-fetched, how can you, isn't this a lot of work to do? Who's going to sit there and twist the dials until we stay on this? Well, of course, there's the whole field of process dynamics and control. And I'll be seeing you there, hopefully, right, next year. So process dynamics and control, the 4th year course, we do cover cases like this where you are trying to control something. So that's what you can do. But I've also, in this class, in previous years, I've done a quick assignment. Let's just have a look at that batch case. So I'm just going to look for one of the previous years where I've had that. Yeah. Yeah, so here we go. So this is an example. If you follow this example, if you don't implement heating or cooling and just let the system react, then you're stuck to a very small conversion here. But if you apply heating and cooling, right, then you can start to track the maximum rate path. So number one, your heating would get you on the maximum rate path quickly, and then you apply cooling to stay there. And let's see, in this one, yeah, we actually do show the maximum rate path line. We've used a preheater, so we're not relying on the heating jacket to get us here. So we used a preheater to start from 450, and then we allow it to react when it gets to there. Then we just apply cooling. So this is generated by this code. If you look at the code that I used to find that solution, here's the ODE, right? Well, that's the integration. Here's the ODE. And here, this is just the problem. It's a reversible reaction. Here's the forward and reverse, and you can see the Arrhenius constants and so on. And here is the control. So it's simply saying, if the temperature is less than the maximum rate path temperature, then apply heating. So apply in the jacket, apply, blast it with a high temperature of, let your jacket fluid be at a high temperature. Otherwise, which means when it's below the maximum rate temperature, when the temperature is greater than the maximum rate temperature, then we want cooling, then apply a much lower temperature here. And if you have a look at this solution, you'll see it's the same non-adiabatic balance, right? You've got your heating and cooling here, and then the rest here, your heat of reaction, your theta I, CPI, all of that is there. So your standard energy balance is here. And the control is, so this is where that control is exerted. You just compare your current temperature in your batch reactor with your desirable maximum rate temperature, and then you take action by applying heating or cooling. So it's as simple as this. Of course, practically doing it is more complicated. Just saying here, make the jacket temperature this or that, is ideal, is an idealization. In reality, there'll be some thermal lag. It will take some time to switch from the one to the other and so on. But if you can at least do this, then it gives you a starting point. When you do this, then you can calculate how much heat you needed to add or remove. Okay, any questions or comments there? Please go ahead.
By any chance, is there a way you can expect us to do it using your code, or every time we expect us to do it manually, not using code?
So, sorry, I didn't quite get what you're saying. It's quite muffled there. Are you asking, is there any way I can expect you to do this, like in a test or exam?
Can you hear me, sir?
Okay, that's much better. Thanks.
I was asking if by any chance we'll be required to do it using code, or all of the time in terms of testing us will be requiring, you're gonna require us to do it manually.
What I could do, like in a test or exam situation, is ask you to sketch just sketch what path you want to follow and highlight certain features and say, okay, at this point, yeah, how do you get to this point? Then you have to explain, I have to add heating to get to here, and then to get to there, I need to do this. So it's more like you would explain your way around that phase plane rather than writing code. So I wouldn't ask you to write code in a test or exam. Yeah.
Okay, thank you, sir.
Okay, thanks. Any other questions or comments there? Okay, if not, that's it for today. We'll of course get more practice doing these things. But next time we'll be talking about nonlinear dynamics and chaos theory as well. All right, so till next week, looking forward to seeing you in person. that's it for today.